So, as was said, I'm Dillon Mulroy. I'm here to talk about Melange today and the next frontier in type-safe web development. So who am I? I am a software engineer at Vercel. You can find me at all the things. Generally, I'm DM Mulroy, except for Twitter. For some reason that was taken. I'm Dillon_Mulroy. Next, there's a bunch of code in these slides, so if you'd rather follow along on your own device, feel free to hit this bit.ly link or scan that QR code. So my goal today is to pique your curiosity and excitement about OCaml, ReasonML, functional programming, and to demonstrate how they can improve the type safety of our applications. So this is kind of what it feels like. Coming to a conference mostly composed of JavaScript and TypeScript developers to tell y'all to not use JavaScript and TypeScript. So what is OCaml? OCaml is actually an acronym that stands for Objective, Categorical, Abstract, Machine, Language. If you're anything like me, I know what those words individually mean, but put together, I have no idea. I don't have a background in mathematics or type theory or category theory or anything like that. And the last time I thought about what that acronym actually stood for, I was shitposting on Twitter. It's only OCaml if it comes from the objective region of France. Otherwise, it's just sparkling categorical abstract machine language. So what really is OCaml? The OCaml.org website describes it as an industrial strength functional programming language with an emphasis on expressiveness and safety. But how would I describe OCaml? I would describe it as a statically typed language with amazing type inference. It is a sound type system where you hardly have to annotate. You don't have to annotate your types if you don't want to. Yet you'll get more type safety than a type system like TypeScript. It's immutable by default with opt-in mutability when you need it for performance critical things. This helps prevent the most common bugs in our applications, those stemming from mutability. It's also blazingly fast. If you're just writing straight up normal OCaml in an idiomatic way, you're going to get close to 50% the speed of C, which might sound bad, but that's remarkably good. You're generally going to have faster runtime performance than languages like Java or Go, but kind of thinking in that same ballpark. Jane Street, which is a major user of OCaml, is working on a fork of the compiler where you'll be able to opt out of garbage collection. So it could end up being a very good replacement for Rust. It's also a pragmatic application of functional programming for the real world. In the time that I've been using OCaml and kind of been in the ecosystem and the community, it's this kind of beautiful mashup of industrial software engineers using it for their day job, and then your PhD programming language academics. And over the past 20 years that the language has been around, the forcing function of those two sides have driven really, really nice APIs and ergonomic features to the language. Community is top tier. When I was learning OCaml, everywhere I went for help, I was greeted with empathy, kindness, and everyone went way above and beyond. And most importantly, at least to me, it's fun and a joy to write. Also, the Twitter memes are pretty damn great. I collected a few to put on display here. Oh no. There we go. Well, they're there. You can check the slides. You can use the bit.ly URL and pull up the slide decks if you really want to see them. All right, so what is ReasonML? Put simply, ReasonML is an alternative syntax for OCaml that is designed to feel familiar and welcoming for people coming from JavaScript or other C family languages. It's completely interoperable with OCaml and its ecosystem. You can have a ReasonML module in one file, OCaml in the other, import them between each other, use the same packages. It's literally just an alternative syntax for OCaml. It was made by Jordan Walk, who is also the creator of React, excuse me. Unsurprisingly, JSX is a first-class citizen in the language and built-in, so you can just start writing your standard JSX in a ReasonML file. As I already called out, it's going to feel super familiar for folks coming from C family languages. So what is Melange? I felt like this is actually like a pretty timely slide, given the release of Dune 2. For those who aren't familiar with the movie and book Dune, Melange is like the spice, like the drug in the movie that everyone's fighting for. Just kidding, but only kind of. OCaml's build tool is actually called Dune, so it's kind of like a little cute play on words there. So what really is Melange? Melange is a compiler for OCaml and ReasonML that emits performant, idiomatic, and readable JavaScript. And in fact, it also was partially named from a French word meaning like a mixture of things. So a bunch of kind of different tools and pieces coming together from the OCaml and Reason ecosystem to compose into a tool to emit JavaScript. So let's take a look at like what a Melange React component look like, right? This is going to be our standard TypeScript component, just a simple card. We're bringing in a third-party library called tail and merge. We have a simple type, nothing too exciting here if you've ever seen React. So this is an identical component in ReasonML. It's going to look a little different, but oh no, bumped HDMI. I believe. Here we go. There we go. So this is an identical ReasonML component, same card. It's going to look maybe a little different, right? We have this weird kind of like annotation that says @React and a module keyword, and we have like this make function rather than render. But like as a whole, this should seem at least approachable and familiar to anyone that's written JSX previously. And this is actually what Melange is going to emit. I often joke that like Melange will emit better JavaScript than I actually write. And in fact, like this JSX runtime stuff, like that's what your JSX is getting compiled down to under the covers anyways. So now you might be asking like, but why? Why do we need like another language that compiles down to JavaScript? Like we have TypeScript, we've had CoffeeScript, PureScript, HyperScript, all the scripts, right? Like why do we need this? And to cover that, I probably need to cover how I ended up as the guy talking about OCaml at a JavaScript conference. And to start with that is my journey into functional programming. I started programming in 2006 after taking a middle school course on Visual Basic 6. Yeah, very great start there. I quickly found Lua and JavaScript. I was writing like World of Warcraft add-ons as like a teenager in Lua. And just fiddling around with websites in JavaScript. Fast forward to 2014, land my first full-time job, and I get thrown into a front-end code base that's using Lodash. And Lodash has this API called the Chain API, and I thought the Chain API was the coolest thing since sliced bread. Being able to put in some data and map, reduce, filter, just like have these immutable pipelines, like blew my mind. I loved it. Fast forward another year, I was a relatively early adopter of React. I started writing React when mixins were still a thing. Class components still very much have a place in my heart. I think React did a lot of good for the front end and JavaScript community and ecosystem by introducing a lot of functional programming concepts. Things like we have immutable data, right? If we want to update our data, we use it through setting state functions, and we kind of isolate our side effects. Then later, one day in 2017, I was sitting at my desk eating lunch, watching YouTube as one does, and I stumbled upon a conference talk by a developer at Facebook named Lee Byron. Lee Byron built and helped maintain a library called Immutable.js. Immutable.js essentially uses these things called persistent data structures under the covers, so you can write like more functional code, but not pay the cost of doing like these really expensive copies of your objects every single time. So that's what Immutable is. And I thought that was also the coolest thing since sliced bread. Fast forward to 2019, I start learning TypeScript and using that for my work and my side projects, and I really fall in love with the idea of static typing. I see the value it brings, preventing a whole slew of bugs. And then more recently, in 2022, I had been working at a job where our entire backend was written in OCaml and some front-end stuff, and even an Excel plugin randomly. And I had never, ever written OCaml before. I hadn't used a real functional programming language in my life, but I've always been a full stack dev. Like I've always been on both sides of that line, and I got hired to do TypeScript on the front end. But if I wanted to contribute in a full stack way, it necessitated learning OCaml and fell in love with the language. So before we go any further, we need to talk about TypeScript. So TypeScript, like OCaml and Reason, is a statically typed programming language. It has excellent tooling. Like we as TypeScript developers have genuinely some of the highest quality tooling across any language ecosystem. Yes, there's a lot of churn, but it enables us to have like a fantastic developer experience once it's working. TypeScript can be gradually adopted. It does have a gradually adopted or a gradual type system. And this is probably a huge reason for its success, right? Like back in like 2016, 2017, we were all either still writing vanilla JavaScript or transitioning into something like TypeScript or Flow. And the fact that we could just like incrementally add types to our code base over time was huge. That coupled with the Definitely Type repo where community members were contributing types for popular libraries, that like really helped TypeScript take off. As I said already, TypeScript enables an amazing developer experience, and just as like a little tidbit, TypeScript was never built for us. TypeScript was built to enable tooling. It was specifically built for the VS Code team at Microsoft. As they were building that, they had a decision to choose between compiling C# to JavaScript or basically building a new superset of JavaScript with types, and they went with the latter. And overall, and like most importantly, TypeScript is a vast improvement over just straight up dynamically typed JavaScript. That being said, let me take a sip of water here before we get to the bad news. TypeScript can be cumbersome and complex, right? When we're trying to model relationships between types, we can find ourselves in a world of like these really nested generics and types with ternaries and type mappers, and it can get really, really complex really, really fast. Because the TypeScript team chose the route of being a strict superset of JavaScript, TypeScript is also burdened by all the warts that JavaScript has because of its dynamism. JavaScript has too many escape hatches, which can create a false sense of safety. And ultimately, TypeScript is unsound. And you don't just have to take my word for it. Anders Heilsberg, who's a Microsoft fellow and the lead architect of TypeScript, gave a keynote talk at the International Conference of Functional Programming this year, or I guess last year, and he said the following quote, "I mean, clearly, this type system is not sound, and it was never designed to be sound, and gradual type systems aren't. They may be sound in islands, but they're not overall sound." He also used this slide to describe TypeScript's. If this goes out again, just like yell at me. Come on. Let's see here. Won't it be a conference talk without technical difficulties? While that's coming back on, never mind. So this was the slide that he used to describe the type system. He described it as erasable, gradual, structural, generic, inferable, expressive, object-oriented, functional, and unsound. Okay, what does unsound actually mean, and why should anybody care? So a type system is considered sound if it can guarantee that a program will not cause certain types of runtime errors, assuming the program type checks and compiles successfully. So what makes TypeScript unsound? Well, we have our usual culprits, right? We have any, type assertions using the as keyword, non-null assertions, typecasts via type guards or type predicates, and or using function overloads. Essentially, if you're using these anywhere in your code base, you're introducing the ability for human error and to encounter runtime type errors. Surely then, if we avoid those features in TypeScript, we'll have sound and type-safe code that won't cause runtime type errors. Unfortunately, not. And let's look at an example here. So let's just imagine this simple application, right? We have like an account type. It just has a username that's a string and maybe like a flag to determine if that user is like an admin, right? Maybe like when we sign in or maybe when they're creating an account, they have this validate username function. It takes an input that has a username string. We validate that it meets some length. If it doesn't, we throw an error. Otherwise, we return the object back out to the caller. You can imagine maybe somewhere else in the code base, maybe like in a utils folder or something, we have this print record function that takes a record and then just iterates over the keys and pretty prints it out to the console, mostly like a debugging utility. And then like you can imagine this is like the actual runtime code, right? Like we make an account, username DM Mulroy, is admin true, we validate our account, and then we can just print it, right? So this code successfully type checks and compiles, even with the strictest settings with the TypeScript compiler, but there's still a runtime type error that it does not catch. So can anybody pick out where the runtime type error is? Bueller? Bueller? Yes. I've given this a couple of times now. You're the first person. It's the first time someone's got it on the first try. So this line right here is going to cause a runtime type problem and either crash our program or cause a try-catch block to get hit, right? So what happens is we have this isAdmin flag, but our print record function is saying, hey, we want to take a record where the key's a string and the values are a string. But realistically, we're passing in a type that's more closer to a record where the keys are strings and the values are strings or booleans. So when we hit this line and try to call trim, which is a string function, it's going to blow up in our face. Right, I guess I should have kept spacing here. So with all that being said, I do genuinely love TypeScript. It has introduced a whole generation of developers to the merits and benefits of static typing and type safety. The TypeScript team is like genuinely one of the most impressive teams in open source. They ship fast, they take feedback well, they're communicative with the community, like just top tier across the board. It has genuinely improved the quality of our applications, code, and experiences for our users. And I also build and maintain two new Vim plugins, tsc.mvim and ts error translator. The first is used to run the TypeScript compiler asynchronously and basically give you project-wide diagnostics. TS server, which is TypeScript's language server, is like notoriously bad at that. And then I've also recently ported Matt Pocock's VS Code extension called TS Error Translator, which basically takes TypeScript's garbage compiler messages and tries to put them in a more human-friendly format. So now we're going to get back to our regularly scheduled programming. So let's take a brief tour of OCaml and ReasonML. So these are the things we're going to cover. And up first is ints and floats. These are going to seem super familiar to what you're used to, right? And that's just like let x equals 6, let y equals 9. We have a sum and a product, nothing crazy. Same with floats. But what might stick out is that our infix operators are a little different. You cannot mix and match types in OCaml and ReasonML. And one thing I should call out, for the rest of the presentation, I'm going to be using ReasonML for the syntax just because it's a little bit friendlier. But all of this still equally applies to OCaml. So because we have to use specific infix operators for our float types, this is like kind of what enables the much stronger type system that these two languages have. And now you may be asking, like, what happens if I try to like add a float and an integer? Well, you're going to get error in your editor and a compile time error that says this expression is type float, but an expression was expected of type int. So next up is tuples. Tuples are basically like fixed length lists or just like bags of data. One nice property of tuples is that you can kind of mix and match the types in a tuple. You're going to see through the rest of my presentation, I'm going to have these comments above a bunch of the code that indicates the type. As I said, OCaml and ReasonML is like almost bulletproof at perfectly inferring types. So I'm just going to label the types up there for us. There's also the language server for OCaml and ReasonML has a feature called Code Lens that you can turn on that will also put these kind of comments above your code so you can see your types at all time. So to start, our first type is a date. It's a tuple where the type is int, int, int. We could also model an address, right? This would be string, string, int. Or maybe we create a type alias for a coordinate that is a tuple of an int. One cool thing is that after we make that coordinate type, the type system knows that it can infer our variable point to be the type of coordinate. So next up is lists. Lists are annotated, basically a list of the data type. It's going to feel like pretty familiar to JavaScript, or TypeScript, I should say. So we can do like let names equals OCaml ReasonML. We can append to a list. We can have a list of floats. Also good to call out with lists, you can't mix and match data types, right? We couldn't have like a float, an int, a string. It has to be all of the same data type. Next up is sum. This is going to be the first function we see in Reason. The type of the sum function is a function that takes two floats and returns a float. Basically the way that the type system can figure this out is the plus dot operator, right? We know that we already covered plus dot can only operate on floats. Therefore, A and B must always be floats. And finally, we have let total equals list.fold. This is going to be identical to your array.reduce function. Basically, we're just going to loop over our scores. We're going to call the sum function on each one, aggregate it, and then return it out. Next up are records. These are going to feel basically identical to our typical TypeScript types, right? Basically just key value pairs. Let's say we have a song, has a bunch of keys with string values, and then maybe we have a playlist, and the playlist has songs. We have a list of songs. This is what we call polymorphic types in OCaml and ReasonML. That is just a super fancy word of saying generics. So let's say we wanted to model an API that requests data from Spotify, right? We're going to use the same song type record, and then let's say we have this like generic API response that takes this tick A thing, which we call alpha. So we're going to say type API response has a status code of int, and then our data is going to be of type alpha. And then our song response is going to be a API response of songs. Forgetting my slides, classic. So this is the identical TypeScript to the previous slide. Basically the same exact thing with the exception of alpha and the type T. Next up is like the first killer feature of languages like OCaml and ReasonML. We have a data type called variance. These are like enums on steroids, and like not TypeScript enums, which like have a some baggage with them. So this lets us model out things like for our response, like we have this yes type, and we can literally use the value yes as like a value in runtime code. So we can say our type response can either be yes, no, unsure. Or maybe we have like a DOM event type in our browser where we have 4 different constructors, right? So the different members of a variant are called constructors. Constructors can also hold or carry data. So let's say we have a click event that holds, maybe the X, Y coordinate of where a user clicked, or a hover event, or maybe a key press that holds the character that was pressed, or we can even have data list constructors, maybe for a window resize. So to amplify the power of variance, we can then pattern match on our variance. And pattern matching is essentially going to it's like switch statements on steroids. Not only can we switch or pattern match on primitive values or runtime expressions, we can also basically match on types too. So let's say we have this function handle event, which the type is being inferred as taking a type event, which we had on our last slide, and it's going to return a unit. A unit is effectively the same type as void in TypeScript. So we're going to get our event, and then we're going to switch on it. And we're going to say, hey, if this is the click event, let's pull out the x, y coordinates and bind them to x and y variable names, and then we can pass that on and do whatever we want with it. So we just pass it through to log click chords. Same with hover. Or maybe we handle a key press and we pull the individual key character that we pulled out. So that's kind of how pattern matching works at a high level. Next up is our result and option types. So this is how we're going to handle errors in OCaml and ReasonML. We don't generally throw exceptions or raise exceptions. We treat errors as values, basically put it on the caller to handle errors where they occur. So our result type is going to be a type that has two type parameters, a OK type and an error type, and then the two constructors are OK of the OK type and error of the error type. This is what this would look like modeled in TypeScript, and in fact, I actually use these types all the time because, quite honestly, I think throwing exceptions is probably the worst feature in JavaScript, and the fact that we can't like statically type them and we can't be certain where our program's flow could be interrupted, I think that's, yeah, it's just not great. But this is exactly what our result type would look like modeled as a discriminated union in TypeScript. So how would we use our result type? Let's say we have a safe divide function, it takes two integers and returns a result where the OK value is an integer and the error value is a string. So we'll say if y equals 0, we're going to return our error variant with a message that just says division by 0. Otherwise, we're going to return out the value of doing division less any remainder. Then you can see we call it, right? Let answer result equals safe divide, 10 and 2. We can see the type being inferred as result of int and string, and then we can pattern match on that to get the type out. You can either say, hey, is this an error? If it is, do whatever we got to do to handle the error, or we can match on the OK value, get the OK value out, and continue on with our program. There's also some syntactic sugar that's a little bit outside the scope of this talk, but we can do these things called let bindings, where we can kind of like create our own let keyword. So we say let OK is going to equal result.bind. And this is going to work almost exactly like our await keyword in JavaScript. This is basically going to unbox our OK value if it is OK. But if it's an error, we're going to immediately return from the scope with the error value. Next up is our option type. This is basically how we handle null or undefined. We basically have either a sum of alpha or none. And you can imagine maybe using this like you're starting up like a REST API server and you read in like a YAML file or a JSON file that has some configuration, right? Like the website's name and like maybe an optional port if you want to override the default. So we say port's going to be an option int. And then we say like our config record is going to be port, it's going to be sum of 8081. And then like maybe later on in the program, for whatever reason, we want to like get the port configuration. We can match on our config.port and we can say if it's none, we're just going to return 3030, our default port, or we can pull out the port that the user passed in. As I've previously mentioned, OCaml and Reason are immutable by default, but we can opt into mutability when we want it. For record types, we can mark keys as mutable, and then we can basically assign on them just like you would in JavaScript. And then we also have refs. And if you're familiar with React in that ecosystem, refs were actually inspired by OCaml. It's going to be the same way. We get our variable.contents, and that is like our mutable reference in our variable, and we can just update that. There's also some syntactic sugar. There's like little array, or I don't even know what that symbol is called. But those two lines are effectively the same exact thing. So my light bulb moment with OCaml and ReasonML occurred when I was building an OAuth callback server. So I started learning OCaml in my free time, and like I was having a pain point at the time where like I was switching from Spotify to Apple Music, and like all the services to transfer playlists either sucked or were really expensive. So I was like, I'm going to do this on my own. So part of that was building OAuth, because both Apple Music and Spotify like make you authenticate using OAuth. So this is the code, and we'll go over this a little bit line by line here. But when you do OAuth, for anyone that might not be familiar, you basically like send a bunch of data to the service you're authorizing with, and you provide them like a callback URL. And like if everything's good with the data you pass them, they'll take that callback URL and effectively call that so it hits your server and you get like a payload with the token. And part of that is like you send server or like this thing called state generally, and it's just like random bits you send along with each request, and then when you get it back, they send the state back with you, and if that's identical, you know it hasn't been tampered with. So that's basically like what this function is doing. And basically the inferred type is it takes a request and a string, and we return a result where the OK value is a string and the error value is just a message of string. So to break this down, let's first look at this outer pattern match here. We're going to pattern match on like the primitive string value of request.path. We're going to say, hey, if this path at runtime equals /Spotify, let's continue on with the program. But if someone tried to hit this running server with any other endpoint, we're going to return an error that says invalid path. Next up is this inner code block. Let's see here. So what we're going to do here is we're going to try to pull off the data that the service has sent back to us. So we're going to use this getQueryParam method and try to pull off a code query parameter and a state query parameter. GetQueryParameter returns an option of string. And the way we can get those values out of that option is by pattern matching again. So we'll match on both of those. And one thing that's super cool, this is like where my mind was blown, is just being able to like so succinctly describe all of the cases in one place. So like if we have a code as a query parameter and we have state as a query parameter, right, so if we have both of the query parameters and the state that we get back from them equals the state we generated for the request, we say, okay, we're authorized, let's take this code and like we know we can start making API requests. Next, if we get both query parameters but the state is not equal, we know that like it was probably tampered with and that's an invalid state. Or maybe we get a code param query parameter but we don't get our state parameter, right? That's a none value. We didn't receive state. And the other option is, hey, we didn't get a code parameter. So like you can handle all these different edge cases just like I think so elegantly. So next we're going to talk about Hindley-Milner. Hindley-Milner is the magic that powers OCaml and ReasonML. It is the type checking algorithm that the compiler uses for inference. So we're going to demystify that and build a basic intuition of how that works. So can anyone tell me what the type of S is? And just like feel free to shout it out here. Yes, it is a string. What about X? Int? It is not an int. It is a string. Now what about Y? False. It is an int. So let's walk through how we figured that out and how the type inference algorithm is going to figure that out for us. Because essentially the way the algorithm works is the way we kind of subconsciously can look at this code and derive that ourselves. So starting with S, I'm going to just like use these question marks in place of like the actual types as we work through this. So starting with this first parameter to foo, it's being passed in as S, and then it gets passed immediately to string.length. And because string.length can only ever accept a string, we can infer that S must be a string. Now the return type of foo, well, we know length will only ever return an int, so we can accurately infer that foo must return an int. Now how about X, right? Well, we've already done the work of figuring out that like foo takes a string and returns an int, right? So we can know that bar and X must always be a string. Next is Y, right? We've looked and we've talked about ints and floats already. The plus operator only ever works with integers, so that's our first hint. And we've also already evaluated foo, and we already know that foo returns an integer. Therefore, Y must always be an integer. And finally, the return type, right? We know that if we're using the plus operator, we have to be dealing with ints, and foo returns an int, and Y is an int. Therefore, the only thing that the return type for bar could be is an integer. So that at a basic level is essentially how Hindley-Milner or algorithm J works on basically doing type inference without any sort of type annotation. This is the same exact, I should say we can also annotate our types. And in fact, I annotate my types in OCaml quite frequently, especially at like module or API boundaries for documentation, or maybe I'm like just like writing out a function and I know ahead of time what I want it to take, what I want it to return, and I want to make sure that the compiler is, you know, being my friend along the process, right? I want it to tell me if I'm not doing the right thing. So let's look at the same code, but in TypeScript. Does anyone know like what the type of S, X, and Y is going to be? No? No guesses? It's going to be any. We're going to get an error. And now you may be saying, well, Dillon, that's not fair. Your string.length function was like explicitly typed to take a string and return an int. Well, okay, let's do that. Womp womp, still any. Because TypeScript's type system is built the way it is, because it's gradual and structurally typed and a whole slew of other reasons, TypeScript just does not have the power to make that kind of inference. So let's get back to talking about Melange and how we can have sound and type-safe JavaScript. So how does Melange work? Melange ships with a bunch of APIs for common JS bindings. So we have our standard library. The Melange standard library is going to essentially be a one-to-one mapping of ReasonML and OCaml's standard library. So like if you just went to, the ReasonML docs, like all of those functions are accessible to you and they will compile perfectly to JavaScript. Same with the OCaml standard library. We have our top-level JavaScript library. This is going to give us bindings to things like promises, arrays, string, JSON, regex, dates, null, undefined, things of that nature. We have our DOM API, which is going to give us bindings to the window, document, events, local storage, anything you can access in basically the browser. We're going to have an API for that will compile to JavaScript. And finally, there is Node.js bindings. So we have access to things like path, file system, buffer, basically the Node standard library. So what if you want to bind to other JavaScript code like NPM packages, or maybe you have just some other JavaScript you've written locally that you want to bind to? Well, Melange has a featureful binding API via this thing called a PPX. PPXs are basically just OCaml and Reason's version of macros. So PPX stands for OCaml Preprocessor Extensions. Basically, it runs code at compile time to generate other code. It's used to, should I just read my point? Use the modifier extend syntax during compile time. It's deeply integrated into the language, runtime, and tooling. So if you use PPXs, you can derive new types, you can derive objects, and your LSP server and your editor will give you those autocompletes, things of that nature. PPXs come in two flavors. Not super important. They're called extensions and attributes. And you can kind of think of a PPX being kind of like Babel. We've historically used Babel to transpile JavaScript that uses ECMAScript standards that aren't shipped to all the browsers yet down to some sort of backwards compatible JavaScript. So it's super similar to that as far as the mental model goes. I'm not going to dive real deep on these slides, but our extension nodes essentially are going to be marked with this bracket % syntax. And at compile time, that's going to get erased away and directly replaced with other code. So we'll have APIs like putting things like the debugger in, or generating regular expressions, or just inserting raw JavaScript if you want. The other flavor is attribute nodes. These are more akin to adding or changing the semantic meaning of your code. So this will be things like, personally, the one I use a lot out of this list is mel.return. So if you're binding to some JavaScript function that might throw, you can just annotate your binding with @mel.return, and it will catch an error and return it in a result type. So let's look at an example of what it's like to write a binding. So we're going to take a look at binding to Tailwind merge, which is basically just a little utility for merging together and deduplicating Tailwind classes. This is what it looks like in TypeScript. And this is our binding definition, which might look scary at first. It's pretty verbose. It's definitely my least favorite part about Melange, but we're going to break this down. So this first part, @mel.module, this basically just is the name of either the NPM package or a relative path to the JavaScript file we're actually going to be writing a binding to. This next bit here, it's not mandatory on everything. It's just for this specific function. Mel.variadic indicates that a function we're binding to takes a variadic or indefinite amount of args. So you can basically just keep doing comma string, comma string, comma string, comma string on tail and merge. So next up is the external keyword. This is a OCaml keyword that basically tells the compiler, like, hey, we're getting ready to interface with like some foreign code that is not OCaml, and in our case, it's going to be JavaScript. The next identifier is going to be the name of either our variable or our function that we're going to call or use in our OCaml or Reason code. The next bit is our type definition. So the type definition of tail and merge is it takes an array of strings and we're going to merge those down into a single string. And finally is the name of the actual function we're binding to. So what does this look like to actually use, right? So we still have the same binding declaration, and then to use that merge function, we can say let merge classes equals merge, pass in our array of strings, and we're off to the races. And this is actually the JavaScript that exact code compiles to. So again, there's the TypeScript, and here's the code that our ReasonML or OCaml compiles to. So how can you get started? The best way, in my opinion, is a tool I built, which is actually recommended by the Melange core team, called Create Melange App. So if you wanted to, you can just run npm create Melange app at latest in your terminal, and it's going to walk you through a wizard of getting set up. Ends up looking like this, so you can choose whether you want to build a React app, if you want to use Vite or Webpack. We're working on adding other bundlers, just a couple options, whether you would rather use OCaml syntax or ReasonML syntax. Yeah, if you run into bugs on that, please file an issue. Would appreciate that. Next up is the Melange playground. So if you were to go to melange.re, there's going to be a link right up at the top that says playground, and you can just get started writing OCaml or Reason in this left pane. In fact, you can toggle between the two to have it convert the syntax, so you can see like what would this ReasonML look like if it were OCaml. And then in the right pane, it's going to output the JavaScript that gets generated. Another fantastic resource, which I'm working on producing like a YouTube series for, is Melange for React devs. It's basically a free book online where you basically go from chapter 1, getting set up and started, to like going through building out React apps using Melange. Oh. What happened? I'm sorry? Oh, I don't know how far back that was happening for, but we'll... All right, so if I haven't piqued your interest in OCaml and ReasonML yet, let me just ask the question quick. How many people are server-side rendering React in here? Anybody? Couple? Good bit? Okay. So... Forward and back. There we go. Thank you. Thank you. Teamwork makes the dream work, right? So there's a really, really good and compelling story to doing full stack React with OCaml and ReasonML. So there is a full-blown implementation of React written in native OCaml. So OCaml that does not compile to JavaScript. The same OCaml that we're getting 50% the speed of C with, where we can use, because ReasonML has JSX and syntax support, we can write JSX on the server, have it run natively with that insane speed, and then use those same components in the browser that compile to JS with Melange. And this is just kind of a diagram of like how that breaks down. Libraries that do this is Reason React, which is what you'll use generally to write React with OCaml or Reason, and then server Reason React, which is like the raw, just native implementation of React. And it's pretty freaking fast. It blows, as you can see by these numbers here, it blows Node, Bun, basically anything else that comes even close to this, like out of the water by like 10x. So like unequivocally rendering React with SSR, which generally like you're doing because you want performance anyways, right? Like maybe you're doing e-commerce and like even that, 80 milliseconds is $1 million every month. Like this can boost your performance even more. So yeah, the TLDR is OCaml is the fastest, most performant, and type-safe way to server-side render React. If you need to get help and you choose to just check this stuff out, some of the best places to get help is the OCaml forums. Both OCaml and Reason have a Discord. And then I'm part of this Discord community of a bunch of functional programming streamers that a lot of us do OCaml content called the Caravan. So you can hop in there and get help. I also stream generally OCaml content every Monday through Friday, 7 a.m. to 10 a.m. And feel free to come hang out and ask questions. Otherwise, let's make the web type safe together. Thank you, y'all.